While we've looked at circular or periodic motion previously, one of the things we didn't really get into was looking at the forces and therefore the accelerations that act on that object as it travels through its circular path. One of the reasons we didn't do that was we really hadn't covered forces yet, so we're now going to go back and revisit circular motion and look at the force that we previously determined must point towards the center if you go back and review your notes. But we're also going to take a look at the acceleration or the resulting acceleration due to that force that points towards the center. Now those actual terms, instead of just force and acceleration, we refer to them as centripetal force and centripetal acceleration. So before we get into those, let's just quickly review what we learned when we went over periodic motion. And that's that at any given point, in this case A, B, or C, the object has what's known as tangential velocity. Due to its inertia, at point A it wants to continue traveling in a straight line. That's directly at point A. At point B, as it's swinging around here, at this particular moment it wants to travel in this direction. And at point C, as it travels around, it's going to want to continue to travel in a straight line. And that's its tangential velocity. That's why if you remove that force at any point, that object will travel in a straight line tangent to the path it was previously traveling in. The other thing we looked at was that there's a force that acts towards the center of that circular path. Now, despite the fact that this object, whatever it may be, at point A would like to go in this direction, point B would like to go in this direction, or point C would like to go in this direction, that object doesn't actually travel in that direction. It continues to travel in a circle. And that's because at every particular instant, A, B, C, any point in between, there's a force that acts towards the center. So if you're trying to go this direction and something's pulling you towards the center, you can see that the blue line, which represents the path you take, is going to be somewhere between these two, because your inertia wants to send you this way, and you have a force pulling you towards the center. So you're going to do something in between, and you're going to continue to travel in this circular path as long as this force is pulling you towards the center. So now let's look at this term centripetal, as in centripetal force and centripetal acceleration. And centripetal quite simply means center seeking. So centripetal force is like saying a center seeking force, a force that wants to pull you or push you towards the center. And likewise, centripetal acceleration is just center seeking acceleration. So while you are accelerating, you're not necessarily accelerating in a straight line as we looked at previously. You're actually accelerating towards the center of that circle. So the one fundamental concept to realize is centripetal just means center seeking and refers to the force that pulls you towards the center of your circular path, and therefore the acceleration that you feel towards the center of that circular path. So one of the most common questions you get when you take a look at this is the fact that the centripetal acceleration is towards the center. And a lot of students tend to be confused by this. And it is a rather confusing concept. In order to really fully prove it, you'd have to mathematically use vector addition, which tends to be a little bit more complicated than we want to look at right now. So I'm going to attempt to give you a little bit more of a conceptual understanding. Again, you'd have to really look at vector addition of the changing velocity. That's something you could certainly look up on your own, or you could ask me outside of class, but I'm not going to go into that degree in order for my explanation. I'm going to give you the more conceptual approach. Now, the thing to realize here is that the acceleration is a vector, which means it has both magnitude and direction. Because what tends to confuse students is if, let's say this is a yo-yo. Let's say a yo-yo is being spun over your head, and this is a bird's eye view. All right, as the yo-yo spins in this direction, at point A it would like to go this way, but there's the force of tension because the string is what's pulling it towards the center. So the force of tension at point A is pulling it in this direction. So while it wants to travel in this path, because of this inwards centripetal force, it's going to begin to curve. And at every point along this blue circular path, there's a centripetal force, in this case the tension, that's pulling it towards the center of the circle. Now this velocity, the magnitude, might never have to change. If I spin this yo-yo at a constant 10 meters per second, a lot of students incorrectly think that it's not accelerating. And the problem comes from the fact that the magnitude doesn't change. They say, well, it's 10 meters per second the whole time, so therefore it can't be accelerating. And that's where we kind of break away from what quote-unquote common sense tells us. Because acceleration is a vector, and we don't usually think of things in life as vectors. So you're absolutely correct. The magnitude would not be changing. But But if you take a look and follow this blue circular path, at every single instant, my direction is changing. And therefore, I do have acceleration. Is my velocity changing? Certainly. Well, is the magnitude of the velocity changing? No, it's 10 meters per second at every point. But its direction is changing. Since its velocity is changing due to change in direction, well, you have a change in velocity over time, and therefore you have acceleration. So, centripetal acceleration just means the object is constantly accelerating, not in terms of magnitude, in terms of direction. It wants to go this way, but it curves towards the center. It accelerates towards the center. As it's at point B, it would like to go this way, but you see it curves towards the center. So think of this yo-yo or whatever object as constantly curving towards the center of this circle, and that's where that acceleration comes from. Change in direction, not magnitude. And again, this goes back to the whole concept of vectors, but this is conceptually as far as I'm going to go into explaining where centripetal acceleration comes from. Just realize that this object, though it might be hard to see or hard to realize, it's constantly curving towards the center of the circle. Its inertia keeps it from traveling straight towards the center, but it is being pulled towards the center, and therefore its direction will change towards the center. So that's where centripetal acceleration comes from. So what you'd have to realize is we should add another arrow at each one of these points, and that arrow or that vector would represent the acceleration towards the center of that circular path. All right, so as I mentioned previously, the object accelerates because it is constantly changing direction towards the center of its circular path. You could also use Newton's second law, which states that the net force on an object equals the mass times the acceleration. And if you think about it, if the net force acts on an object to the right, that object is going to accelerate to the right. If that net force acts down, the object will accelerate down. So it makes sense that since the F net in this case acts towards the middle, well, just like those other examples, the object will accelerate towards the middle. So two different ways. You can use Newton's second law to kind of explain how that net force causes that center-seeking acceleration, or if you realize that the direction of that object is constantly changing towards the center, another way of understanding a little bit better how this acceleration exists towards the center. Now at this point, most students, if they kind of digest that information a little bit and they think about it, they do tend to see what's going on. However, there's quite another misconception that tends to pop up. And again, that's because these are not really everyday topics that we're discussing right now. So a lot of students tend to put two and two together and then say, okay, so I see now. We have things like friction, tension, gravitational force, etc. Centripetal force must be this new force. So it's the force that pulls things towards the center of a circular path. And while that's kind of right, it's not exactly right. There's a little bit of a misconception there. And as soon as students find that out, they usually tend to feel a little bit like this because they kind of just finally felt that maybe they realized what was going on with centripetal force, centripetal acceleration, what's going towards the center, what's going tangential. Don't feel too bad though. There's just one small adjustment you have to make. Centripetal force is not a new force. That's the key here. It's not an actual force. Friction is an actual force. Gravitational force, an actual force. These are actual forces that could act on you or an object. Centripetal force is not like an actual force. Centripetal force is quite simply any other real force like friction, gravity, tension, or a combination of forces, maybe gravity and tension, tension and normal force, that act as the centripetal force. So much like an actor will play a role, centripetal force is like a role that another real force will actually play. So the actual real definition of centripetal force, which we represent as an F with sub C, it's really the net force acting towards the center of a circular path, and it's required to produce circular motion. If an object is traveling in a circular path, there must be a centripetal or center-seeking force acting on that object. That's not a real force. It's like a new force. It is a real force. It's not a new force. Centripetal force is not something that you'd add to your list of known forces. It's a role that one of those other known forces acts as. So just to show you a few quick examples, consider a car going through a curved section of a roadway. So based on this arrow, it's traveling in a clockwise direction. Now, even though this isn't a complete circle, since it's traveling through a curved path, that is demonstrating circular motion, at least while it goes through the curve. So before we even consider anything, we know that if it's traveling in a curved or circular path, then that's a centripetal force requirement. There must be a center-seeking force that acts towards the center of this path. So we know that there must be a force pointing towards the center of the circular path. And now we just have to say, well, what actual force acts as the centripetal force? Well, if we think about it, friction is what keeps your car going through a turn. If you eliminated the friction, such as maybe the roads were icy or there was like an oil spill, you can hopefully realize that car is going to have a much more difficult time navigating that curve. So in this case, friction is the centripetal force. If we look at a second example, we look at the moon as it orbits the Earth. Well, that's a circular path. We know the moon travels in a fairly circular orbit around the Earth. Well, if it travels in a circular path, there must be some kind of force pointing towards the center of this path. That's what keeps it going in a circle. Well, if we think about what we know about the moon and Earth, we know that the gravitational force of the Earth pulling on the moon, that must be the centripetal force. It's acting as the centripetal force. These are two a little bit more simpler examples. There's only one force that acts as the centripetal force, but it's important to realize that you can have cases where you have maybe a combination of forces. So let's pretend you're on this roller coaster and you're going through a loop. Now you know that as you're on the track, there's a normal force from the track. There's also gravity that's pulling you down. There's probably some friction and other forces. But let's just look at the forces at the top of the loop. As you're at the very top of the loop at this instant, you have the normal force from the track, right? That's the reason why you're not flying in this direction or this direction. The track is pushing you down. It's keeping you from flying off. But you also have gravity pulling you down. So in this case, the combination of that normal force from the track and the force of gravity, they will combine, and those two together give you a net force acting towards the center, which is the definition of centripetal force. So just realize that actual forces that we've already learned can either act solely as the centripetal force, or they can combine to form the centripetal force. But centripetal force is quite simply a net force, either a singular force, a combination of forces, a net force that acts towards the center of a circular path. If you have an object traveling in a circle, there must be a centripetal force. If it's not traveling in a circular path, it does not have that circular motion. Lastly, if we want to look at these mathematically, we have centripetal acceleration formula and the centripetal force formula. You can see we use A sub c to represent centripetal acceleration, and we have F sub c to represent centripetal force. Centripetal acceleration is quite simply that tangential velocity squared over r. And r is just the radius of that circle, or the distance from the center. So if you want to know how fast something is accelerating towards the center of its circular path, you take the tangential velocity squared divided by the radius, or the radial distance, how far that object is from the center of its circular path. To calculate centripetal force, well, we just need to go back to Newton's second law. We know that F equals ma. Therefore, it's not too far of a leap to think that the centripetal force, it still equals ma, but it just equals mass times centripetal acceleration. So net force equals mass times net acceleration. Well, centripetal force equals mass times centripetal acceleration. If I just plug in my v squared over r for my centripetal acceleration, we get our centripetal force formula, which is just Fc equals mv squared over r. It's just F equals ma, but I've substituted centripetal acceleration for acceleration, or our normal general acceleration variable. So these are the two equations we'll use to analyze centripetal force and centripetal acceleration mathematically. The last thing, please don't forget, put this in your notes somewhere, this is what trips up most students. While this equation is helpful, it's only really helpful about 70 to 80% of the time. The other 20 to 30%, we can't forget that centripetal force, not only is this equation true, but it can also equal the force of friction, or the normal force, or tension, or whatever other force acts as the centripetal force. So just to give you a very brief example without numbers, let's say we were analyzing a car traveling through a curved section of road. Well, again, it's a circular path, so we know that there must be a centripetal force acting towards the center. What we'd have to realize here is, well, what force actually acts as the centripetal force? Well, in this case, it's friction. Friction keeps the car going through the curve, so that allows us to then say the centripetal force equals the force of friction, which also equals our centripetal force calculation, and it allows us to relate some information that we might not have known otherwise. So in an example like this, a lot of students will have the force of friction, but if they don't make the connection that the force of friction is the centripetal force, they don't set up this equation. They basically have this on the side over here like, well, it's known information. I have the force of friction. But then they come back to this equation and say, well, I don't have centripetal force, and I might be missing a variable. This problem is not solvable. The key in a lot of these problems is that the centripetal force is probably already known. You've probably calculated it as some other force. So please don't forget, if you don't realize that the centripetal force is the same as some other force or combination of forces in a lot of these examples, you're going to miss this step, and you'll feel like a lot of times you're missing a variable. So don't forget, mathematically, here's how to calculate them. But more importantly, if you forget this step or you forget this little key, you're going to run into a lot of difficulty with these problems.